Good morning guys, and welcome to today's worked exam answer video. Now, following on from my video yesterday where I chatted through all things shapes of molecules, I thought it would be useful to post a worked answer question regarding shapes of molecules so that you could see how I would put into practice what I covered in the video that I posted yesterday. And if you haven't seen the video that I posted yesterday, then you might want to have a watch of that before you watch this video. Or if you watch this video and think, ooh, not really sure what she's talking about there, it might help to go back and watch yesterday's video. So that's up on my YouTube channel. If you search Miss G Tutoring and Resources, I'm sure you'll find it. Or it should be on my TikTok page as well. So in this question, which is an AQA AS question from the paper 1 from 2023, we have a 6-marked question. Now this 6-mark question is one of those levelled marked answers whereby there is some indicative chemistry content provided where they've broken it down into 3 different stages. In this case it's the name of the shape for stage 1. For the second stage it's explaining the shape, and for the third stage it's explaining the bond angles. And in order to get either 5 or 6 marks, we need to be giving nearly every single point in that list, which might be more than 6 points. It's probably going to be about 7 or 8 for this question, but sometimes it could be up to 10. Yes, it feels a little bit harsh, but there should only be 1 of these per paper. So what I'm going to do here is I'm going to obviously answer the question. I'll talk about the different stages. I'll probably split up my answer into those 3 different stages because this is again a question where they're actually looking at our quality of written communication, as it used to be called. Nowadays it's thinking about presenting the information logically, not kind of flitting kind of between ideas, not going back to something that you've already said and re-saying it. So thinking about being concise, thinking about having a nice flow to your answer, and also they'll be looking at your use of keyword terminology, making sure you're using those correctly. So I'll try and kind of point out all of those things as well as we go along. But I think this question naturally lends itself to quite a logical answer anyway, because we've been given 2 molecules and we have to discuss the difference between the shapes of them, and then it says in your answer you should name each shape, explain each shape, and explain the bond angles within each of the molecules as well. So it does lend itself quite nicely to a logical answer. So we've got CF4 as our first shape, and we've got XEF4 as our second shape. So if you were watching my video from yesterday, if you've seen it, or you know, at any point before watching this video, then you will understand the method that I'm about to showcase here. If this method doesn't make sense and you want to learn more, like I say, you can watch yesterday's video. If you are happy with deducing the number of bonding pairs and lone pairs without using my method, then of course do it the way that you know, that you're comfortable with and familiar with. But what I would be doing here for CF4 is finding what group carbon is in on the periodic table, because that's our central atom. So carbon is in group 4, and that means that it's going to have 4 electrons in its outer shell. I then consider what bonds we've got. We've got 4 carbon to fluorine bonds, and in each of those bonds, each fluorine will give, or share rather, 1 electron, and the carbon will contribute the second electron. If there's 4 of them, carbon's going to be contributing 4 electrons, 1 to each of the 4 bonds, so it's going to be using 4 electrons. And if it only has 4 electrons, that means there are no electrons that are not involved in forming bonding pairs. From this information, we can figure out that there are 4 bonding pairs because we've got carbon bonding to 4 separate fluorine atoms. And if there's no electrons left over, there can be no lone pairs. And this is where after we've applied this method, we then need to know off by heart the name of the shape that has 4 bonding pairs and no lone pairs. We would need to be able to obviously explain the shape. That's what we're going to be asked to do here. And we also need to explain the bond angle. So again, we need to know what the bond angle is in this particular shape. So at this point, I'm just going to name it here as tetrahedral. And what I was thinking I would do before I started this question is that I would kind of go through and do the names of both of the shapes, then explain both of the shapes, and then explain the bond angle. But actually, I think it lends itself more nicely to focusing on this shape first and then doing the next shape. So in terms of explaining the shape, that partly comes down to the number of bonding pairs and lone pairs. So this has a tetrahedral shape because there are 4 bonding pairs of electrons and no lone pairs of electrons. So I've covered the first bullet point and I've covered part of the second bullet point. Now in terms of explaining the shape, if we only have bonding pairs, it's good to make reference to the fact that the bonding pairs are going to want to orientate themselves as far apart as possible. Because just because it has 4 bonding pairs, that doesn't mean that you won't have sort of your central atom and kind of have, you know, all the bonding pairs looking like that. It still has 4 bonding pairs, but that doesn't explain why it's a tetrahedral shape, because that isn't a tetrahedral shape. So it's the fact that the bonding pairs of electrons are going to repel each other equally. So that's what I'm going to go on to mention now. So these bonding pairs repel one another equally and orientate themselves as far apart as is possible in 3D. Now some of that is also therefore going to be explaining the bond angle in each of the molecules, and this is where this is one of the reasons, why I changed tack and thought that it'd be better to talk about one molecule first and address all the bullet points, because I've kind of already explained why the bond angle is going to be what it's going to be, because I've talked about the fact the bonding pairs are going to repel each other equally, so all the bond angles are going to be the same, so there's only one bond angle in a tetrahedral shape. And I've also said that they're going to orientate themselves as far apart as is possible in 3 dimensions. So again, if you watch yesterday's video, you'll have seen that a common initial thought for what we would do with 4 bonding pairs would be like that, where that molecule would be flat in the plane of the paper, so you'd have a 90-degree bond angle in here. Actually, by orientating themselves in 3 dimensions, we can get them slightly further apart. The bond angle goes up to 109.5. So again, by saying that they orientate themselves as far apart as is possible in 3 dimensions, I've kind of already addressed that. So my next sentence is going to be, this gives bond angles between each bonding pair of 109.5 degrees. Again, that's because we're working in 3D, but I've already said that. I've already said they want to orientate themselves as far apart as is possible in 3D. So So I don't really think there's anything more I can say about that, because the 109.5 comes from the 3D nature and the fact that the bonding pairs repel one another equally, because it's bonding pairs repelling other bonding pairs of electrons. So I think that's probably it for what I can say about the CF4. So now I'm going to do the exact same thing with the XeF4. So xenon is a noble gas, so it's in group 0. However, it's not got 0 electrons in its outer shell, it's got 8. And we used to call it group 8, and then it got amended, upgraded, changed to group 0. But for the purposes of the way that I will work out shapes, we need to be thinking about the noble gases as being in group 8, so that we know that it's got 8 electrons in its outer shell. Again, I'm then going to consider what bonds we've got. We've again got 4 bonds between xenon and fluorine this time. So again, in each of those covalent bonds, the xenon's going to share one, the fluorine will share one back. So in total, xenon will be sharing 4 electrons, one with each of the 4 fluorines. So 4 of the electrons it has available are being used in those 4 bonding pairs. That means if we started with 8 electrons in the outer shell, that there are 4 electrons that we have not yet accounted for. And these leftover electrons tell us how many lone pairs there are. So there were no lone pairs here because there was no electrons left. However, we've got 4 electrons left here. So in total, there's going to be 2 lone pairs. And don't forget, these do need to go into pairs, so it'll either be 0 electrons, no lone pairs, 2 electrons would give us 1 lone pair, 4 electrons here is giving me 2 lone pairs, 6 electrons, 3 lone pairs. Once we've got that far, then again, this is where we need to just be able to recall really quickly, 4 bonding pairs and 2 lone pairs, that means the shape is going to be, and it's going to be square planar. And being able to draw upon that knowledge really quickly is going to be important. And again, understanding why it is square planar is going to be important, and knowing what the bond angles are is going to be important. So this xenon tetrafluoride has a square planar shape because there are 4 bonding pairs of electrons and 2 lone pairs of electrons. Now, we're going to have to give more information in this answer about where those lone pairs of electrons are going to orientate themselves in relation to the bonding pairs. We're also going to need to talk a little bit more about the electron pair repulsion theory to be able to show that we understand that the lone pairs are going to repel each other the most and then repel the bonding pairs more than the bonding pairs can repel each other. And then think about the effect that the lone pairs have on the bond angles as well. I also think it might be worth mentioning that a square planar shape is based on an octahedral shape, 6 pairs in total, 6 bonding pairs, the shape would be called octahedral. So that's a good starting point for us then thinking about, well, where are we going to put the lone pairs and where are we going to put the bonding pairs. So I think that's where I'm going to go next. So this shape is based on an octahedral shape, but the 2 axial bonds are replaced by lone pairs. Again, if you watched the video yesterday, you'll know what I'm talking about in relation to the axial bonds. Those are the ones that we draw kind of vertically up and down, like the Earth spins on its axis. So axial, kind of your up and down ones, vertical, the ones around the middle, again, a bit like the Earth, we call them the equatorial bonds, like the equator. I think that's the clearest way to explain where those lone pairs are going to go. So it's based on octahedral. We can't call it octahedral because we name it based on where the 4 bonding pairs are. We always name the shapes based solely on the bonding pairs, not the lone pairs. And also we don't have 6 bonding pairs, we only have 4, and we've got 2 lone pairs now, so the shape is going to be different. The lone pairs go in the axial positions because they want to get as far apart as possible, and in an octahedral shape the bond angles around the middle are 90, and then the bond angle between the vertical and the horizontal is also 90. But if we have the lone pairs top and bottom completely directly opposite each other, then they get to be 180 degrees apart. So that's why we put them there. That also is going to help us to explain the shape. So that's what I'm going to do next. So this shape is based on an octahedral shape, but the 2 axial bonds are replaced by lone pairs. The lone pairs want to be positioned as far apart as is possible, which here is 180 degrees because lone pair repulsion is the strongest. So you're not going to want to be putting your 2 lone pairs in 2 of the kind of middle equatorial positions where they're only separated by 90 degrees, because then they're going to really not be happy and are going to want to repel each other far more than that. So 180 degrees is the furthest we can get them apart here, and that is because of the octahedral shape that we're basing this on, and also because of the lone pair repulsion being the strongest. So in terms of explaining the shape, I think I'm now going to address the bonding pairs in a really similar way to what I did with the lone pairs, and say the bonding pairs of electrons orientate themselves 90 degrees apart in the equatorial positions, hence the name of the shape being square planar. And the only other thing I can really think to say, but I'm not sure I need to, is if we've got our lone pairs kind of at the top and bottom of here, and our other bonding pairs are horizontal around the middle like that, separated by 90 degrees, this lone pair here is going to repel the bonding pairs, so you might expect these ones to kind of droop down a little bit, but then you've got the lone pair at the bottom, which is going to counterbalance that by pushing the bonding pairs back up. It's going to want to push them further away from itself, but again that's going to be counterbalanced by the lone pair up here, so that's why the bond angles stay at 90 degrees around the middle. How can I say that concisely is the killer question. The bond angle remains 90 degrees as repulsion by the lone pair above is counterbalanced by the repulsion from the lone pair below. I think that works. Now, please don't be thinking, oh my goodness me, she's written that way more concisely than I would have been able to do, and she's gone over the lines that were provided. You were given a whole extra page of lines. So I only printed this page, but then there was a full another page of lines. So even though, yes, I have gone slightly over at the bottom here, I would have easily got that on the next page of lines. I would not have to have filled all of the lines, and that is something that's really key. It's always quantity over it's always quality over quantity. Definitely always quality over quantity. My apologies. So don't feel you need to write any more. I've answered all of those points for both of the shapes. So, well, for both of the molecules in terms of their shapes. So there would be nothing more for me to say. Anything else that I would say would be repetition. It would stop the flow of my answer, which would affect my ability to get the higher of the 2 marks in whatever level I got to. I might start using terminology incorrectly. Yeah, so once you think you're finished, even if you haven't filled all the lines, not necessarily a bad thing, okay? Hopefully that helps in conjunction with yesterday's video. If there's any questions, however, please feel free to ask them in the comments or drop me an email at missgtutoringandresources@outlook.com. Thank you so much, guys. Take care.